Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are talking about real quadratics with delta the discriminant less than 0 as we listen to the classic rock band The Cars and one of my favorite songs, Let's Go. Let's get to it, shall we? Alrighty then. So, we've been solving quadratics, and we were in the real number system only, and we were saying that when the discriminant, b squared minus 4ac, part of the quadratic formula, housed under the square root, was less than 0, we have no real solutions. And this poses a problem. But we have solved that problem actually in 1572 by our good friend Raphael Bombelli, and he defined the imaginary number I equal to the square root of -1, which led to the complex number system. Complex numbers are of the form a plus bi. A and b are real numbers, and I is equal to the square root of -1. And we have either talked about all of that in class or we shall. So let's get to it, shall we? I've got several examples to do because now, boys and girls, we are able to solve equations where the discriminant delta is less than 0. So, very easy one here. We have x squared equal to -4. So we would find the square root of both sides, plus or minus the square root of -4. Now I have a negative under the square root, and up here I'm just going to say, recall, if I can print any better than that, I is equal to the square root of -1. And I'll only take this step, I think, on this example, because after that it just becomes unnecessary. And this is the step I'm talking about. I can rewrite this as plus or minus the square root of 4 multiplied by the square root of -1, because 4 times -1 clearly is -4. So we simplify that and we get plus or minus 2 square root of 4, and the square root of 1 is equal to I. So we have the imaginary solutions, plus or minus 2I. So let's see what happens with b. Z squared plus z plus 2 is equal to 0. And we're going to have to use the handy dandy quadratic formula because that is not factorable. So z would be equal to -1 plus or minus the square root of b squared 1 minus 4 times a times c, which is 1 minus 8. All over 2a. A is 1, so that's going to be 2. Clean that up. We get -1 plus or minus root -7 over 2. And again, this is the last time I'm going to do this step. -1 plus or minus the square root of 7 times the square root of -1 over 2. And henceforth, I'm going to go straight to this step. -1 plus or minus root 7 I all over 2 are our solutions, which of course we could write if we needed to. Doesn't really matter as two individual fractions. This of course is in the form a plus bi, complex number form, where a is -1/2 and b is root 7 over 2. Again, the step I'm going to skip is right here, in that once I see the square root of a negative number, I know that I can rewrite it as square root of -1 and just write it as I. Okay, write as a product of linear factors. Well, what we have to be thinking here is right now we are unable to write it as the product of linear factors. Usually if we had something like a squared minus b squared, we can always write that as a plus b times a minus b within the real number system. But now that we have complex or imaginary numbers, we can do the same because we can rewrite x squared plus 4 as x squared minus 4i squared, because we're going to recall that I squared is equal to -1. So a -4 times a -1 is equal to a +4. Well, now I have the difference of two squares, so I can use this algebraic formula and get x plus 2i times x minus 2i. So we have satisfied by writing it, satisfied the instructions by writing it as the product of linear factors. In the complex number system, of course, but still, we're now able to do this. Same idea, b squared b. Now, 11 is not a perfect square, but we are not afraid of that. We can rewrite that as x squared minus 11i squared. Again, -11 times -1 is +11. And we can just rewrite that as x plus root 11i times x minus root 11i. Bam! What? So we have some powerful tools at our disposal. It just seems like some mundane algebra right now, but it becomes very useful as we progress. Solving real quick, x squared equals -9. X is equal to plus or minus square root of -9. And this is where I'm talking about we don't need to write out that step of writing that as a square root of 9 times a square root of -1. We should immediately be able to write that as plus or minus 3i. X cubed plus 2x equal to 0. I can factor out an x, and then I get x squared plus 2 equals 0. ZPP! You better have said, yeah, you know me. All right, x equals 0, or x squared plus 2 equals 0, x squared equals -2, x equals plus or minus the square root of 2i. So we actually have 3 possible solutions. One real solution and 2 complex solutions. Moving on, just a few more examples here. Solve for x squared minus 4x plus 13 equals 0. It is not factorable, so we would use the quadratic formula. And just for time's sake, I'm not going to go through the quadratic formula. I'm going to get it to its simplest form, which would be 4 plus or minus the square root of -36 all over 2a, which in this case is going to be 2. Again, I'm not going to bore you with going through -b plus or minus b squared minus 4ac. I know that you know how to do that. This happens to be quite the nice perfect square. So this is going to be 4 plus or minus 6i over 2, which we can rewrite as, let's see, 2 plus or minus 3i. So again, we have 2 complex solutions. You could write them individually as well, but this is fine too. Okay, so b, x to the 4th plus x squared plus 6 is equal to 0, which of course we can write as, or hopefully you see that we can rewrite this as x squared plus 3, oops, that's not a plus, hopefully you caught that, that's a minus, times x squared minus 2. Again, ZPP, so we get x squared equals -3, or x squared equals 2. So x here would be equal to plus or minus the square root of 3i, and x here would be equal to plus or minus root 2. So within the real and complex number systems, we have a total of 4 solutions, which we were not able to do before without imaginary numbers. Okay, I think, let's check. Yeah, that is it. I certainly hope that you enjoyed it. I know I did. And until next time, we'll see you, and we'll go out with more of the Cars' legendary song, Let's Go. And I am out! She says, let's go.